Welcome to Unit 10, Video 4, Phase Diagrams. By the end of this video, you should be able to define key points on a phase diagram, such as triple point and critical point. You should be able to use a phase diagram to determine the phase of a substance given temperature and pressure values. And you should be able to use a phase diagram to determine the temperature at which a phase change will occur, given a pressure value. A phase diagram represents the phases of a substance as a function of both temperature and pressure. Recall that we've been talking in class about the fact that the phase of matter is not just temperature dependent, it's also pressure dependent. Since we pretty much live life at the same pressure all the time, we don't really see pressure affecting phases very often. But if we do vary the pressure, the temperature at which something is a solid, liquid, or gas may vary. This phase diagram here is a generic phase diagram. Notice there's no temperatures or pressures on either of the axes. What you should notice here is that the phase diagram is divided into three regions: a solid region, a liquid region, and a gas region. You'll also notice that the lines dividing these regions represent the points where phase changes occur, as indicated by the arrows crossing these regions, here and here. So any point on a line represents a phase change. The pressure and temperature coordinates of those points on the line will tell us the temperature and pressure at which that phase change is occurring. There's some important points that you should be able to identify on a phase diagram. As we go through these points, it might be helpful to have a phase diagram in front of you. If you go to the haiku page, you'll see that there's a page of phase diagrams that you can print out. The first one is a phase diagram for water, so we'll be looking at that one first. Normal boiling point, as we've said, is the temperature at which the vapor pressure of a substance is equal to 1 atm. We can locate the normal boiling point on a phase diagram by finding the point where the liquid-gas line hits 1 atm. Looking here at this phase diagram for water, we can see that 1 atm falls right here. If we follow this pressure coordinate across to the liquid-gas line, we find that the normal boiling point for water is, not surprisingly, 100 degrees Celsius. Next, we have the normal melting point. This is the temperature at which a substance melts at 1 atm. Again, it's where the solid-liquid line hits 1 atm. Looking again at our water phase diagram, we see that if we find 1 atm and follow it across till we hit the solid-liquid line, we see that water freezes. The normal freezing point, or the normal melting point of water, is 0 degrees Celsius. Next, we have the triple point. The triple point is the temperature and pressure point where all phases exist in equilibrium. In other words, there's an equilibrium between solid, liquid, and gas. This might sound kind of crazy to have all three phases existing at once. We'll look at a video of this in class. It doesn't happen very often. Looking at our water phase diagram, we see that the triple point occurs right here. It's the point where the solid-liquid line meets the solid-gas line and the liquid-gas line. So the triple point for water is at a pressure of 0.006 atm and a temperature of 0.01 degrees Celsius. So you have to have this exact pressure and temperature to achieve this equilibrium between all three phases of matter. Finally, we have the critical temperature and the critical pressure. The critical temperature is the temperature above which vapor cannot be liquefied, no matter how much pressure you exert on it. In other words, at that temperature, regardless of the pressure, the substance will be a vapor. Likewise, the critical pressure is the pressure required to liquefy a gas at the critical temperature. We can combine these two coordinates and call them the critical point. This is the critical pressure and the critical temperature as a series of ordered pairs. Looking one more time at our phase diagram for water, we see that the critical point lies up here. It's generally the point where the liquid-gas line actually ends. So we see that the critical point for water is 218 atm and 374 degrees Celsius. In other words, at 374 degrees Celsius, 218 atm of pressure are required to liquefy the gas. Above 374 degrees Celsius, no amount of pressure will liquefy the gas. It will remain in the vapor phase. Let's look at a phase diagram for a different substance. Notice that this phase diagram is not labeled. When you receive an unlabeled phase diagram, your first step should be to label the solid, liquid, and gas regions of the graph. So let's do that together. The solid region is going to be the lowest temperatures, the liquid region will be the next higher temperatures, and the gaseous region will be the highest temperatures. So the phase regions always go in order, solid, liquid, gas, from left to right. Now we know where our solid liquid line is, where our liquid gas line is, and where our solid gas line is. Pause the video here and try to determine the triple point, the normal boiling point, and the normal melting point of this substance. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that this substance has a triple point of 0.5 atm and negative 10 degrees Celsius, a normal boiling point of 140 degrees Celsius, and a normal melting point of negative 15 degrees Celsius. A few more important points about reading a phase diagram. First, it's important to know that you can find places where the solid and liquid are in equilibrium and where the liquid and vapor are in equilibrium. These points occur along the solid-liquid line and the liquid-gas line. So the solid-liquid line, any of these points along this line, represent equilibria between solid and liquid. Any points along these lines, this line represents an equilibria between liquid and gas. And also, any points on these lines represent equilibrium between solid and gas, a little less common. We can also find melting or boiling points at various pressures using the axes. For instance, instead of finding the normal boiling point of this substance, suppose I want to know the temperature at which this substance will boil at, say, 70 atm. Looking at 70 on our pressure axis, if I follow this across till I hit the liquid gas line, I find that this temperature will boil at about 650 degrees when the pressure is 70 atm. Likewise, suppose I want to know the normal melting point at, say, 80 atm. Again, I find 80 atm, follow it across till I hit the solid liquid line this time since I'm looking for a melting point, and I see that it melts at approximately 425 or 30 degrees Celsius at 80 atm. We can also use a phase diagram to determine what phase the substance will be in at various temperatures and pressures. Suppose I want to know what phase this substance will be in at 50 atm and 300 degrees Celsius. I find the point representing 50 and 300, and I see that this point lies in the solid region of our phase diagram. This tells me that at 50 atm and 300 degrees Celsius, this substance will be a solid. Pause the video here and see if you can figure out what phase this substance would be in at 80 atm and 600 degrees Celsius. Welcome back. You should have said liquid. Notice that this substance at the point of 80 atm and 600 degrees Celsius is in the liquid phase. That brings us to the end of this video. Let's review our goals. First, we defined the key points on a phase diagram, such as triple point and critical point. Then we used a phase diagram to determine the phase of a substance at given temperatures and pressures. We also used a phase diagram to determine the temperature at which a phase change will occur, given a pressure value.